The Hubble Space Telescope. We know it for the galaxies it has captured millions of light years away and for countless nebulae filled with star formation. Since its launch in 1990, Hubble has carried out nearly 2 million observations. From iconic objects like the Eagle Nebula and the Pillars of Creation to the deepest views of the universe ever taken, these observations have been so powerful that they have contributed to more than 22,000 scientific papers. But Hubble's story didn't begin with images like these. It began with one of the most expensive and tragically ironic mistakes in the history of astronomy.
The conclusion we've come to from that is that there's a significant spherical aberration that appears to be present in the optics.
Earth's atmosphere. The reason stars seem to twinkle in the night sky, and a complete nightmare for astronomers. That twinkling means the light coming from the universe is being distorted as it passes through Earth's atmosphere. That's why the idea of placing a telescope beyond Earth's atmosphere is older than most people think. Long before anyone could even imagine traveling to space, the German rocket scientist Hermann Oberth already understood that there was only one way to overcome this problem. In 1923, decades before the first satellites were ever launched, Oberth proposed the idea of a telescope operating in space in his book, The Rocket into Interplanetary Space. But turning that vision into reality would take many more decades. The technology of the time simply wasn't advanced enough to catch up with his ideas. In 1946, American astrophysicist Lyman Spitzer came forward with a realistic and detailed plan for a space telescope. But this plan for a space telescope wasn't just an engineering challenge, it was also a test of patience. To make it real, Spitzer spent nearly 30 years persuading both the scientific community and the government. By the 1970s, NASA and the European Space Agency finally joined forces to turn this massive idea into reality. The goal was clear from the start: a perfect space telescope with a 3-meter primary mirror. When funding began in 1977, the telescope already had a name: Edwin Hubble, whose discovery of the expanding universe reshaped modern cosmology. During construction, budget constraints forced a critical change. The telescope's primary mirror was reduced from 3 meters to 2.4 meters. The size was smaller, but expectations remained extremely high. The astronomy community waited with excitement for this new space telescope, a machine believed to unlock the deepest secrets of the universe. But no one knew what was coming. After nearly 70 years of dreaming, after the work of hundreds of engineers and scientists, and after a $1.5 billion project, Hubble finally sent its first images back to Earth. This was the result. No one could have imagined something this bad. As you can see in these images, Hubble was unable to focus properly. A $1 billion space telescope that simply wasn't working as intended. Like all professional telescopes, the Hubble Space Telescope is a reflecting telescope. It uses a large mirror to collect and focus light from distant objects. That primary mirror is 2.4 meters across and weighs 828 kilograms. Thanks to its Cassegrain design, Hubble is lighter and more compact than most telescopes of similar size. This made it ideal for launch into space. When we say Hubble is a reflecting telescope, we're not talking about a simple mirror. Even in amateur reflecting telescopes, the surface of a mirror is polished with extreme precision, down to a fraction of a wavelength of light. The imperfections on that surface are often smaller than 1,000th the thickness of a human hair. Hubble's primary mirror represented the absolute extreme of industrial and scientific precision. It had to be the smoothest and most accurate surface ever produced at the time. To achieve this, the 2.4 meter mirror was polished for months to an unprecedented level of smoothness. To understand just how smooth that surface was, let's put it into perspective. If we scaled Hubble's 2.4 meter mirror up to the size of Earth, the highest peak or the deepest valley on its surface would rise only a few centimeters. But for Hubble, even that was not enough. The mirror's curvature had to bring all incoming light to a single focal point. To achieve this, engineers relied on a specialized measuring device called a null corrector. This device acted as a reference. It checked whether the mirror's surface had reached the exact curvature it was supposed to have. This is where the real problem was. Inside the null corrector, a single lens was positioned just 1.3 millimeters off. It was installed incorrectly. As a result, the measuring device was giving the wrong feedback. It told engineers that the edges of the mirror needed to be polished just a little more. Unaware of the error, the engineers did what any rational team would do. They trusted the instrument and shaped the mirror accordingly. The error was just 2.2 microns, about 1/50th the thickness of a human hair. Hubble's primary mirror was supposed to bring all incoming light to a single point on the secondary mirror, but because the outer edge of the mirror was slightly too flat, the light hitting that outer edge was reflected to the wrong focus. Instead of converging at one point, the focus was spread out. And that is why Hubble's images appeared blurred. In astronomy, this kind of optical error is called a spherical aberration. So when we say the Hubble Space Telescope was short-sighted, we're not using a far-fetched analogy. A very similar problem occurs frequently in the human eye. If the shape of the eye's lens or cornea isn't perfectly regular, light entering the eye can focus at multiple points, which results in blurred vision. As humans, we solve this problem easily with glasses or contact lenses. And in fact, NASA decided to do exactly the same thing for Hubble. The Hubble Space Telescope needed glasses. The problem was that Hubble was no longer on Earth. It was already in space, orbiting 547 kilometers above the surface and moving at 27,000 kilometers per hour. NASA had two options. One option was to accept this $1.5 billion telescope as one of the most expensive mistakes in history. The other option was to do something no one had ever done before, to fix a space telescope in space.
And we have a go for main engine start. 5, 4, 3, 2, 1. And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
In 1993, NASA launched the Space Shuttle mission, known as STS-61. It was a rescue operation. The 7 astronauts chosen for the mission spent months training on full-scale replicas of Hubble inside massive water tanks on Earth, rehearsing every movement and every bolt again and again. And on December 2nd, 1993, the Space Shuttle Endeavour launched to save Hubble. Of course, the astronauts couldn't replace Hubble's primary mirror in space. The telescope's complex design made that impossible. But that same complexity also provided more than one possible solution. Although the problem was in the mirror, Hubble didn't rely on a single optical element. It was equipped with cameras and scientific instruments designed to capture the light collected by the primary mirror. The most important of these was WFP-C1, the Wide Field and Planetary Camera, often described as the telescope's main eye. However, this camera had been designed to work with a perfect mirror. Once the mirror turned out to be flawed, WFP-C1 could no longer perform its job properly. That 2.2 micron error effectively blinded this camera. So the astronauts removed WFP-C1 and replaced it with WFP-C2, a new camera designed to compensate for the mirror's error by correcting the light in the opposite direction. Of course, WFP-C2 wasn't the only instrument aboard Hubble. The telescope also relied on spectrographs and specialized cameras to analyze light across different wavelengths. Without fixing them too, Hubble could never reach its full potential. That is why NASA engineers developed a system called COSTAR. You can think of COSTAR as an optical correction unit about the size of a refrigerator. Inside it were multiple small mirrors. The system contained 5 pairs of corrective mirrors mounted on deployable arms. Some of these mirrors were smaller than a coin, yet once installed inside the telescope, they functioned like tiny eyeglass lenses, correcting the incoming light. The STS-61 mission lasted a total of 11 days and involved 5 spacewalks, each lasting between 6 and 8 hours. Alongside WFPC-2 and COSTAR, Hubble's solar panels, gyroscopes, and several electronic systems were also serviced. The mission cost NASA more than $600 million, but when it was over, Hubble had an entirely new view of the universe. To test the repair, engineers chose a comparison target, the Messier 100 galaxy, located 55 million light-years away. The images made one thing clear: Hubble's vision problem was finally fixed. However, the Messier 100 galaxy had been selected only as a post-repair test target. About 16 months after the servicing mission, on April 1st, 1995, Hubble was pointed toward the Eagle Nebula. There, it captured one of the most iconic images in the history of astronomy: the Pillars of Creation. Before Hubble, Earth's atmosphere had prevented us from seeing nebulae with this level of clarity. But in this image, the dark, pillar-like structures formed by cold hydrogen gas and dust were revealed in unprecedented detail. Although they appeared cold and lifeless, Hubble allowed us to clearly see regions filled with the raw material from which new stars would eventually form. Launched with a mirror that couldn't focus properly, Hubble had now proven itself to be one of the most powerful scientific instruments ever built.